Hello, everyone, and welcome to today's Hypatia Colloquium series. My name is Evgenia Pinkia. I'm going to be a host of today. Before moving to the exciting part of the talks, I would like to give some notes. First of all, the Hypatia Colloquium series is dedicated to early career scientists and not only provides them a great opportunity to actually share their exciting research among all of us, but also it's a great recognition for the scientific contribution and work. So I would like to congratulate both of the speakers of today for being part of this colloquium series. Going to some technical details, I would like to remind all of you that this event is both recording and live streamed on YouTube. So if you feel uncomfortable about it, I would encourage you to quit Zoom now and rather follow the event on YouTube. If you have any questions, you're free to do so in the end of every talk. This is going to be, the chairs of every talk is going to regulate the discussion, about 5 to 10 minutes per talk. So you can do that if you're on Zoom by raising your yellow virtual hand, or if you are on the YouTube, you can use a live chat, and then we will make sure that your questions are going to be transferred to the speaker. Let's move to the exciting part. This is the schedule of today. We have two speakers, two exciting talks, one given by Emma Bordier and the other from Riccardo Arcodia. I will be chairing the first talk by Emma, and another ESO fellow in Garching, Paula Sanchez, is going to chair the second talk of today. I can stop sharing my screen, and Emma, please go ahead to share your screen and start whenever you're ready.
Okay, can you see my screen?
Yes.
And can you hear me well?
Yes.
Okay, cool. So I will start. Good morning or good afternoon, everyone. My name is Emma Bordier, and I am currently enrolled in a co-supervised PhD. My home university is Leuven in Belgium, but right now I am at ESO Chile, where I am finishing my third year at the end of the year. So today's talk is going to be focused on the formation of massive closed binaries. And I will more explicitly talk about the migration scenario that I am testing on a sample of premium sequence stars. So to pace this talk as better as I can, I will first give you some scientific context about young massive stars in astronomy. Then I will explain the current challenges and goals that are involved in this field. Then I will describe my data set and the technique that I have been using for the purpose of these questions. I will present you some results, then connect this binary formation to the general picture of star formation and give you some takeaways. So let's start with the scientific context, massive stars in the universe and our galaxy. So massive stars are very powerful machines. They are known to have contributed to the reionization of the early universe. And the first generation of massive stars have also contributed to the formation of the very first galaxies. They drive the chemical and dynamical evolution of all the galaxies, and especially ours. There are studies of great interest, especially with the advent of gravitational wave detection and facilities over the past years, because they end their life in powerful explosions, and as such, they are progenitors of neutron star black holes, objects that are also creating these gravitational waves. So when they end their life in supernova, the massive star hits and enrich the surrounding gas clouds and trigger the new generation of star formation, which is the cycle of life. Now, if I can paint the portrait of a massive star, so what I call a massive star is a star that has the initial mass greater than 8 solar mass. So this mass of 8 solar mass has been set because from this mass, winds and ionization start to have strong effects on the environment of massive stars. And also it's the limit for core collapse depending on the mass loss. And obviously starting from 8 solar mass, the feedback for the galaxy is tremendous. And on top of that, a very important characteristic of massive star is their multiplicity. In fact, more than 90% of OB type stars are in multiple systems. And multiplicity plays a pivotal role in the evolutionary path of massive stars and hence the orbital parameters. So now if I can focus a bit more on this multiplicity, different studies have been done over the past years to characterize this multiplicity fraction in different populations of massive stars, depending on their evolutionary stage. So first, the studies have been done among a population of massive stars on their main sequence. They have found that binary interaction dominates the evolution of O-type stars for more than 90%. And going a bit further, they found that a third of high mass stars are part of a triple star system or even higher order multiple system. Then, using direct measurements of the orbital parameters, Sana and collaborators found high tendency towards short period binaries. And in fact, 40 to 50% of OB type binaries have a period of less than a month, which is very short. Then the same kind of study has been done on a population of premium sequence stars. And the first one was done on M17, these young clusters that I will talk about a bit later. And they measured the radial velocity. In short, radial velocity measurements relate to the presence of close companions. A large radial velocity would refer to a close binary. And on the other hand, radial velocity dispersion indicates the variety of binaries that populate the cluster. For example, if a cluster has several close binaries of similar masses, one would expect the individual radial velocities of the stars to differ significantly from each other, and therefore for radial velocity dispersion to be large. A dispersion of 30 to 50 kilometers per second is common in older clusters. So spectroscopic survey has been done in M17 over 11 premium sequence stars, and they found a low radial velocity dispersion. So there were two main assumptions for that. The first one was a low binary fraction, but if we lower the binary fraction to meet this low radial velocity dispersion, it would challenge the previous derived binary fraction done for the main sequence population. And it would suggest that M17 is a very atypical region. So we most likely tend to accept that there is a lack of short period binaries in M17, meaning that we have more long period binaries. Now, if you see this very interesting graph, that is a very recent result that has been proposed by Maria Claudia Ramirez-Tanes in 2021. What you see here is the radial velocity dispersion against the age of the cluster. And the black line represents the best fit of the data. The radial velocity dispersion is higher as the cluster gets older. In other words, the results indicate an increase in the fraction of closed binary systems as the clusters get older. If you see the data point of M17 seems to be a unique cluster given its very young age and extremely low radial velocity dispersion, and as such will be the object of the present study. But before I present you this very interesting star forming region, I would like to highlight this discrepancy that we have between premium sequence stars and main sequence stars. So the early measurements for the premium sequence phase have been converted to physical periods and showed a big contrast between premium sequence and main sequence binary periods. We do not know what happens between these two stages, and as such, it raises some questions about the formation process of closed massive binaries, and it's mostly where my projects come in. So how do we form these very close binaries? This is where the migration scenario comes from. So it suggests that binaries are formed at large separations, and then they harden over a time scale of 2 million years or less to match the observations that we see in the main sequence phase. So this migration scenario can happen mainly in two different channels. The first one is that the companion will interact with the surrounding gas of the binary system, the circumbinary gas or disk, and will interact with it and harden and move towards the central star. The second channel would be the interaction with an outer star. Mainly because massive stars are formed in clusters, so it's really it's likely that they will be surrounded by another companion, and the first companion will interact with the second companion. There will be some gravitational interactions that will make the orbits to shrink and will leave the central system as a very close system. So those two channels act to reduce the orbital periods of stars and then to observe these very close systems. So the main questions I will try to answer here is, what are the multiplicity properties of massive stars at the latest stages of their formation? And this will help us to discard or confirm this migration scenario. So now that you have some general scientific context, I will jump to the observation of young massive stars, because my results are mainly based on observations for the moment. So to observe young massive stars, first you have to choose a suitable population of young massive stars. And as I said before, M17 and its central cluster NGC 6618 are very good candidates for that purpose. And why? It's because M17 is a great star-forming region located in the Carina Sagittarius spiral arm, and it's one of the closest, most luminous, and youngest star-forming region in our galaxy. So there is high chances that we can catch massive stars at the earliest stages of their formation process. So the sample was taken from the central cluster that is inside this M17 star-forming region. The cluster is called NGC 6618 and is known to host the most massive stars of the region, the M17 region. So the dataset is composed of 6 young O-type stars. They were the brightest ones, with K-band magnitude ranging from 7 to 9. And previous spectroscopic studies have shown that they are of luminosity class 5, meaning that they have probably reached the zero-age main sequence already. And also because we cannot have any signature, or in the spectra also we don't see any feature, any signature of disk or accretion disk around these stars. And if we account for the previous companions that have been found, 5 spectroscopic companions were reported in the literature for these 6 young objects. Then once we have the object of the study, we have to define the wavelength, the technique, and the instruments for the observations. So you have to know that detecting young massive binaries is very challenging, mainly because young massive stars are deeply embedded in their dusty cocoon when they are forming. They usually peak around 100 micron, meaning that we have to observe them in infrared if we want to maximize the flux that we can get from them. Then we would like to resolve binaries or triple system from 1 milliarcsecond to 100 milliarcsecond to test for the migration scenario, because we expect to find companions within the expected size of the accretion disk, which is more or less 200 AU. So we need high angular resolution for that. And knowing that the these objects are observable in the southern hemisphere, we also need southern hemisphere facilities. That's why we went for the VLT and VLTI. And the best compromise was to observe these stars using near-infrared, K-band, obviously, interferometry with gravity. And we used the unit telescopes rather than the auxiliary telescopes, given the faintness of the stars that we are observing. So now that we have all of that in hand, is that to say the object, the technique, the instruments that we want to use, we can build the proposal, request time to ESO, and it's what we got. So we got the observations of the 6 stars with gravity. So now if I can explain you a bit more what we get from interferometry. So we have 2 main observables that are the visibilities and closure faces. So if we focus on the panel where you can see the data, the left-hand panel shows the closure face of the object B98. The closure faces, they trace the asymmetries in the system. For example, a different brightness in the binary system, or the presence of an asymmetric disk, or all these kind of asymmetries that you would expect in a system. Then the right-hand panel, you can see the visibility amplitude. So the visibility measures the fringe contrast. And unresolved point source will have high contrast fringes and a normalized visibility amplitude of 1. For a spatially resolved object, you would expect like a decrease in the fringe contrast and therefore a drop in the visibility amplitude. So when your visibility reaches 0 or around 0, it means that you completely resolve the components. So by measuring this drop in the fringe amplitude, astronomers can measure the size, the shape, and the surface features of a star. And this is what we have done using the PMOARED tool that has been developed by one of the colleagues at ESO Garching, Antoine Méran. So this is a tool on which you can build your geometric model, and you can fit it to the data. It's what you see in the graph in black, the black or black dotted line. So my purpose is to get the multiplicity properties of this object. So I either fit a single star, a binary, a triple, even higher order multiple systems. And for that, I use these building blocks. I built my model, and the fitted parameters are mainly the position of the companion and the flux ratio with the central star. So I have done all this process for all the 6 stars, and these are the results. So it happens that all of the systems are multiple systems. We found 3 triples and 3 binaries. So now I will explain the physics that is coming out of these observations. And this slide sums up the major and main results of my paper, the multiplicity fraction and the companion fraction. So all of these 2 concepts have been compared with different populations of stars from 0.1 solar mass to 40 solar mass, more or less, regardless of the environment and evolutionary stage or age of the sample. What matters here is the multiplicity fraction given a mass range for the primary star, or the companion fraction given a mass range for the primary stars. So if we look at the multiplicity fraction graph on the left, and we focus on the upper part of the graph, you can see my data point, the work over M17 in red, and this has been compared to the data point of Sana et al. In 2014, where the population was limited to O dwarfs, and also the very recent work done by the Gravity Collaboration on Orion. What is very interesting is that my result is compatible with the results of the Gravity Collaboration and also the results of Sana. If we look at the right-hand panel, the companion fraction, so accounted for the spectroscopic companion that were reported in the literature, we derived a companion fraction of 2.3 companions on average. And this also has been compared with other populations, and it's really interesting because it's really compatible with the other results. What is different would be the error bars, but it's mainly because we have a small sample and the gravity collaboration with Orion as an even smaller sample. Another very interesting result would be the separation to the primary star, because if we would like to test this migration scenario, we need to know where the companion is located around the primary star. So what you see here is the resulting brightness contrast as a function of the companion separation in milliarc seconds. We have also overlaid other interferometric campaigns, the one of SANA 2014 done with Pioneer, and the one of Gravity for Orion. So we can see that companions span a wide range of separations from few milliarc seconds to almost 100 of milliarc seconds. This is a preliminary result that may contain biases, so would need to be evaluated in detail, but the first conclusions we can draw is that no significant relation between the magnitude difference and the separation is noticed at that point. There is a clear lack of detection below the magnitude contrast of 2, and companions located within 3 milliarc seconds. This is mainly due to the sensitivity of Pioneer and Gravity. So what we can see from this graph is that if we combine interferometry with other techniques to probe either closer companions, for example, with spectroscopic campaigns, or wider companions, for example, with high contrast imaging, we would have like the big picture of the environment of massive star from very close vicinity to wide. Cool. So now that you have seen the main cosmic signal that rises from these results, I will give you some hints about the binary formation in the general context of star formation. So it seems very clear that high mass stars predominantly form in stellar clusters as opposed to in isolation. But yet an observational sequence of massive star formation is lacking. While it is possible for low mass stars, we have like snapshots of almost every stages of the star formation, while it's not the case for massive stars, mainly because they have the formation time scale is very short, and also because they are bloated in their envelope, so we don't really know what is going on inside this envelope. But three main scenarios have been proposed to explain the formation of massive stars, mainly because we don't know where the mass comes from to form such very big cores. The first one would be stellar mergers and collisions, but I will discard it from now, at least for M17, because M17 is not dense enough. The stellar content is not dense enough to allow these collisions and mergers. So then remains the competitive accretion scenario and the monolithic collapse. The main difference between these two theories.
Sorry, five more minutes. Sorry.
Oh, okay, thank you. Thank you, Evgeny. The main difference between competitive accretion and monolithic collapse is whether the gas is bound to the core or not. So if you look at the upper panel, the monolithic collapse is that scenario in which a massive star originates from the collapse of a dense and massive core that contains the mass reservoir available to form the star. Then if you look at the upper part, the competitive accretion scenario, so the gas will inflow from larger scales due to the cluster potential into the cluster center where there is a higher gas density. So the star in the center accretes more and is fed by this gas inflow and will likely become the most massive stars of the cluster. So now that you know how to form more or less one massive star, we need the companions to be formed and to create this binary or triple or even higher order multiple systems. So the companions, we don't really know how they are formed. So probably like due to disk fragmentation around these massive stars, or either like the massive central star can capture some companions. So this is also still unclear how we get a companion around massive star. So now if we come back to M17, so the wide range of properties obtained among the M17 population in terms of separation and masses does not allow us to identify a single or mostly dominant formation mechanism. Nonetheless, it is worth mentioning that given the young age of M17, which is less than 1 million years, some dynamic processes may still be undergoing, and that the final stellar content and structure of M17 is not set yet. So the migration processes inside M17 might still be underway as well. The wide range of separations and mass ratios might illustrate that the stellar population did not reach the expected time to draw the final structures. And if the migration scenario is correct, we indeed expect that most of the objects have at least one detectable companion within the expected size of the accretion disk, which is the case in our modest sample. So now I will give you quickly the future project, present the future projects and give you some takeaways. So we have results about the multiplicity properties on main sequence, pre-main sequence. Now I would like to know if these results that we found in M17 extend to the very young objects and if it extends also to the earlier stages of massive star formation. And this has been done recently, very recently, by two main studies. The first one is by Pomoati in 2019, where they used a population of massive young stellar objects. So they observed it with K-band adaptive optics imaging with NACO, and they found a binary fraction of 53%. And another work that is more recent has been done by Evgenia Kumpia. She observed also a sample of MYSOs using K-band interferometry with gravity. She could detect some inner disk rings, meaning that they are very young objects, and she could derive a binary fraction of 17%. So to answer the same question as the ones with M17, but in earlier stages, I am right now working on a project with NACO imaging data, where we have a sample of 13 MYSOs from different regions in our galaxy as well. And the goals is the goals are to study the multiplicity as we did for M17 and as they did as Pomoasi did with other MYSOs, and we would like to know whether these results match with the ones of Pomoachi. Yes, and very recently, I also got time to observe 14 MYSOs in M17. So in our initial proposal, there were 20 targets, but only 6 were observed because of bad weather and technical issues with gravity. So only the brightest ones could be observed, hence the most evolved. So I was allocated time in priority A for the ongoing period P109 to observe 14 MYSOs in M17. And these ones are the most inclined to show the outcome of massive star formation in terms of multiplicity and orbital properties. So we wish to catch the processes that shapes the binaries and see how it looks like in the actual formation process and what we can learn from the earlier stages. So the last slide, some takeaways. So 100% of multiple system at the zero image sequence in M17 with 2.3 companions on average at the traced scales, meaning up to 120 AU for gravity. Despite the cluster environment and age, M17 shows consistency with the previous studies in terms of multiplicity and companion fraction for the O-type star population. The concepts of monolithic collapse and competitive accretion cannot straightforwardly result in what we observed. We will be able to better constrain the models with more observation using different techniques also. Thank you for listening.
Thank you very much, Emma. That was a really nice result and very nice talk, very clear. Are there questions for Emma? I don't see any hand raising, but maybe I can start. For me, it's very fascinating to see that your face value already from what you observe is 100% multiplicity. So I was wondering if you can say a little bit more about how the sources were selected, and if you think that because of being a part of binaries or multiples, somehow gravity prefers to pick them up over other objects.
Okay, yes. So as I said in the latest slide, the original sample was composed of 20 targets. Mainly, they were selected given the previous spectroscopic campaigns. So in that sample, they were mainly massive young stellar objects, which is the objects that we want to catch. But unfortunately, only these 6 objects that were the brightest one were observed and were the most evolved of the sample. Then, yeah, it's really surprising that we find the 100% multiplicity, but like we have very reliable results with gravity. We tested like different geometric models. We also tried to add some complexity to know whether we can find any signature of disks or so, but unfortunately we cannot find disks. This is also a good hint on this also tells us that these objects are more evolved. Yeah, and that's why we would like to now observe the youngest ones to know if we also find this this high multiplicity rate or not.
Thank you. Looking forward to see what you get there.
Yes.
So next question comes from Dietrich Bade. So Dietrich, feel free to switch on your camera and address your question.
Yeah, thank you. Very nice talk. I enjoyed that. Until say 20 years ago, star formation models were 1D, and it was impossible to form stars with a mass more than 10 solar masses. And stars only formed in models when they went 2D or 3D, and they could simulate instabilities. And your results suggest that not only prefer massive stars to be formed in multiple systems, but it's perhaps even impossible to form single massive stars. So can one combine these two things and can say that whatever the instabilities are that permit the formation of a massive star automatically lead to the formation of multiple systems?
Well, I have to study a bit more like the theory of this massive star formation, but it's clear, I think, that most of the massive star first they form in clusters and not in isolation. And yeah, like the main question about this star formation would be where we get all this mass to form this very massive cores. So yeah, from now I don't have the hints about that, like how we can reconcile these two channels or paths. But I hope that with more data about the massive young stellar objects, we will find the likeliest channel. Because it's likely also that among the very young population of massive stars, we will not find any companions within the expected size of the disk. That means that we can discard that the companions are formed around this, and maybe that capture would be the likeliest channel to have these companions. Yeah, but for sure, like I have to look a bit more in detail about these theories of massive star formation.
Okay, thank you.
Thank you. I don't see any more questions coming up. Just on YouTube channel, we have a great job, Emma from Abigail Forrest, and I agree, great job. Well done. I think we're running a bit out of time, so maybe we can go to the next speaker, and I will pass the chair to Paula.
Thank you.
Hi, thanks. So the second talk will be given by Riccardo Arcodia. He got his PhD last year from MPE, and now he's working as a postdoctoral fellow there. So please, Riccardo, you can share your screen now.
Yes, thank you, Paula. And I'm sharing the screen now. Okay, and thank you, Paula, again, and thanks to the organizers for giving me this chance. And today I will present a new type of X-ray transients related to accretion onto massive black holes that have been called quasi-periodic eruptions. I will go first through an introduction. Let me start with this statement that most or all the galaxies contain a black hole at their center. Observationally speaking, most of them are undetected at most wavelengths. They are either dormant overall or hidden between the emission of the host galaxy, behind the emission of the host galaxy. And in the X-rays in particular, you wouldn't detect them. But then some of them are active and would outshine the emission of the galaxies they reside in, basically as all wavelengths. And we would detect them as point-like X-ray sources. And after 56 years of X-ray astronomy, we think we know what the average accreting supermassive black holes looks like. And we essentially have been seeing since the early days fast variabilities, fast variability on short timescales. And also, even if we think about the most extreme cases, we can see from supermassive black holes fast and high amplitude variability occurring over a few hours of time, like in this panel here, or over years, even decades. But this is what it would look like. It would look like a continuous type of variability, even if it reaches high amplitude of a factor of 10 or 100 over a few hours. And then a couple of years ago, we saw this coming from the nuclei of galaxies. Essentially, people have been seeing quiescent emission from some galactic nuclei, and then high amplitude bursts occurring in a quasi-periodic fashion. And they call these events quasi-periodic eruptions. I'm going to start giving an overview about these objects. And for instance, I've mentioned that these X-ray blasts are coming from nearby galaxies, so they are extragalactic events, but they're not the typical active galactic nucleus or AGN whatsoever in any wavelengths. For instance, they don't show broad lines in the optical spectra. They don't show infrared colors of typical AGN that suggest the presence of a dusty torus. Instead, if one collects the optical spectra of the QPs, they simply show narrow lines, and sometimes in the bottom example, they're barely visible, and only when the host galaxy is subtracted. So what we can conclude if one performs the classic line diagnostics from the optical spectra, where in such a plot on the bottom left, you will find galaxies in which ionization is dominated by star formation, and on the top right, when it's dominated by the AGN. And apart from two of the 5 QPs that we know of so far, you can see that most of them lie somewhat in between. Therefore, what we can know at the moment, what we know is that there is some degree of ionization in excess to star formation. We don't know whether the QPs themselves can ionize narrow lines, but for sure this is not a typical AGN, because these nuclei don't look active in any wavelength. For instance, even by these diagnostics, one can say that they were active 10 to the 5 years ago when using the narrow line region timescales. but they are now doing these crazy flares in X-rays. So at least the inner region around the massive black holes is now very, very active. And one thing that we know from observation is that these X-ray blasts are coming from black holes which have very small masses, 10 to the 5 to 10 to a few 10 to the 6 solar masses, which is not typical for normal AGN. In fact, we are almost scratching the high mass end of the intermediate mass black hole population, perhaps. And if one puts it into context, comparing all the other galaxies in AGN, we know this is the classic plot comparing the black hole mass and the stellar mass in the galaxy. And you can see that most of the sources are at the high mass end, and the green circle is where QPE's sources would be, which is in fact scarcely populated because these sources are usually faint, undetected, and unnoticed. But we get to see at least a few of them because they show these recurrent flares in X-rays. So these are not normal active nuclei. Perhaps they're getting active now. Perhaps these are massive black holes awakening, and maybe this is a phase in which the massive black hole is using the snooze button and wants to go back to sleep. But eventually, we might see signature of normal active nuclei in some time. We don't know that yet. Another important thing is that we know 5 QPE sources so far, and they were all discovered through X-rays. They don't seem to do much at other wavelengths. And if one combines their overall observational properties in one table, it will look like this. So the average separation between 2 bursts in the same source can range from a couple of hours to almost a day. They would last from about half an hour to a few hours. And then the luminosity that these events would reach are 10 to the 40 or 10 to the 41 in quiescence and 42, 43 at the peak. So these luminosities are consistent with them being massive black holes at around 10 to the 5, 10 to the 6 solar masses. And another important point to make is that most of these 5 sources were found either serendipitously or through searches in the archives. All but 2. And I'm going to expand a little more on that because it's a project I've led, and it's currently the only systematic way to find more QPEs. In our team, we have been using the Rosetta X-ray telescope to find more QPEs. I'm going to just very briefly describe what it does and what it is, because the audience is broad. You don't need to do much. It's just a great X-ray telescope with a large field of view, which is scanning the whole sky continuously. It's rotating around the ecliptic. It's at L2, and therefore it has an orbital time around the ecliptic of about 4 hours. So every source in the sky is observed a few times every 4 hours, and then never again for 6 months, which is what it takes to do a full sky map. So just to make an example, if we want to find QPEs with Rosetta given this sampling, imagine now that there is a source undergoing QPEs in the sky, and we can try and find it with Rosetta. If we manage to catch this source with an amplitude pattern as follows. For example, we detect the source in one scan, then 4 hours after we don't, and then we detect it again, and then we don't. And in this way, if we find sources like this, and of course we can narrow it down with other diagnostics, but this is the idea, this can provide candidates for quasi-periodic eruptions. And this would be the only way to find new ones as they are happening now. And in fact, what we did was to perform this search in the first year of Rosetta data, and we found 2 QPEs, which were later confirmed. And now on the top panels, you see basically what I've described in words, which is the Rosetta light curve. You see there is a pointing every 4 hours, and the source was faint and bright, then faint, bright, and then faint again. And the same for the second candidate. They were both associated with galaxies, so they were extragalactic events. You can see in red the position uncertainty with Rosetta and the optical image of a galaxy. And then when we performed X-ray follow-up, we confirmed that these were indeed QPEs. And an important point to make here is that if you see the top panel, so what Rosetta would see was pretty similar in the 2 cases. But if you then see the bottom panels, you notice that the timescales are really different. So on the left, the baseline is 11 days of data. and on the right is 1 day. And the average periodicity on the left is almost a day, and on the right it is a couple of hours. So with DROSITA, we managed to sample completely different timescales of about a factor 10. And in fact, we did find the one with the lowest and the highest period among the 5 that are currently known, and which is good. It's a very promising method, and in fact, the only one that can provide new candidates. Interesting, but I didn't tell you what they are. Most of it because we don't really know, but there are a few ideas, and I'll tell you a little bit about the one that is currently pursued the most. Let me first briefly comment on a couple of scenarios which are currently disfavored. For example, we have currently disfavored a scenario in which there is an isolated massive black hole with an accretion disk which undergoes some accretion instabilities without an external trigger. And we have also disfavored the scenario of a binary of black holes of the same mass, say 10 to the 6. I don't have time to go into too many details about this, but you can read up more in this paper. And in particular, I want to focus on the scenario that is being really used the most at the moment. And it is the so-called extreme mass ratio spirals. In particular, you can picture 10 to the 6 massive solar mass black hole and one or more stellar objects around it. Now, there are several flavors, even if one restricts themselves in this particular scenario. For instance, somebody proposed a star being partially stripped at every pericenter passage, at every passage. Some other authors have proposed collisional interaction between a star and a compact accretion disk. And there is another alternative model in which there are 2 stars orbiting in the same plane around 10 to the 6 black hole, and which are counter-rotating, and they interact among themselves and provide additional matter to the black hole. Now, these so far have only compared qualitatively with observation. So we cannot say that this is the correct scenario yet. It seems like it's the right direction, though, based on a few elements. For example, I've told you that these are around massive black holes, around 10 to the 6 in low mass galaxy, around 10 to the 9 solar mass in stellar mass. And this is where one would expect to see nuclear star clusters, and this was confirmed for a couple of sources observationally. And also, among the 5 host galaxies of the QPs, there is a high incidence of post-starbursts. And both these elements would enhance the rates of interactions between stellar objects and massive black holes in the nuclei of galaxies. So perhaps we're going towards the right direction. Moreover, among the 5 TD QPE sources, 2 of them have evidence of a decade-long decay in the X-ray light curve. This is just an X-ray light curve of one of the sources over 10 years. And no QPEs were found for about a decade until 2019, when they were first discovered. So this source was already bright before QPEs were found in their data. And somebody suggested that this might be reproduced by a tidal disruption event from the envelope of these stellar objects. And then after some years, the remnant of this disrupted envelope is now interacting with a compact accretion disk, causing the QPEs. We don't know whether this is true or not. It could be a good idea. One thing that we know for at least two of the 5 known sources is that these eruptions here have disappeared after a few years. So they are not a long-lasting event. If you think about the usual timescales of a galactic nucleus, these are transients. Another interesting point is that if this is the correct scenario indeed, these systems could also emit gravitational waves. And in fact, these extreme acceleration spirals, these MRIs, should be detectable by future generation of detectors. And we don't know whether these systems would be able to emit both gravitational waves, detectable gravitational waves, and electromagnetic emission, because the presence of an accretion disk might prevent the system to reach an orbit which is close enough to produce gravitational waves detectable by LISA. But these are early days. And if this is the correct scenario, and we can actually detect the gravitational waves from these systems, then this has huge implications for future synergies between, for example, Athena and LISA. Now, one thing that I didn't say is that QPs are not only a quasi-periodic collection of bursts, which people then have been modeling with orbital phenomena. They are more complicated than that. Therefore, if you are a modeler out there, and if you want to model QPs, you need to know that they are more complex than they seem. For example, this here is an X-ray light curve, and if one then puts to zero all the event peaks, for example, and they're now all superimposed, they look very similar, but the dashed line is half of the distance in time between the event peaks, and it's systematically before the intermediate peak. So, for example, there are at least 2 sources out of 5 that show this scatter in the period, which is very specific, longer and shorter separations. And these you can probably fix with some eccentricity in this orbital phenomenon. But some other QPs show very complex variability. And for instance, now you see one example that I've showed before of this light curve, which is long, about 11 days. And now if we look at the same source, but with a deeper instrument, X-ray instrument, so 2 observations which are long by about a day each, we see that the same source underwent a single isolated burst in one of the 2 exposures. And then a week before, it underwent a very chaotic mixture of different bursts with different amplitude. And therefore, at this point, if we want to really test models against QPs, we really need to go further and not model their quasi-periodicity, but rather everything that they show to us with the available data. Now, I want to go through a quick summary before taking questions, if any. And I've shown you that QPs are this new exotic X-ray phenomenon related to the Black hole accretion. They're not only this because they might provide us with a new channel through which the nuclei of low-mass galaxies are activated, which is interesting, I guess, for a wider audience. We only know 5 so far because it's a very brand new science case, which was born a couple of years ago. And in our team, we have found 2 systematically using the Eurosita X-ray telescope, which doesn't seem much, but as I mentioned, we have doubled the sample with this method. And I'm currently now looking into the second year of Eurosita data to try and find some more. And this is currently the only way to find systematically new ones as they happen, because people have been looking through the archival data, and probably we have found the ones that were there. Well, I'm not sure, but probably. And just to give you a summary of what they could be, the origin scenario is still unknown, so you can still go out there and propose new models. What people are trying to test at the moment is a high mass ratio binary. And so far, so basically a 10 to the 6 solar mass black hole and 1 or more stellar objects orbiting around it. Comparisons so far have been qualitative. They can reproduce the overall average luminosities and periodicities, but there is a lot to do to really know physically what is causing these eruptions and their complicated multi-wavelength properties. And I hope I gave you a good teaser about these QPs. Feel free to jump in this field with new data and new models. I would be happy to see your papers. And I'm happy to take questions now if you have any.
Thanks, Riccardo. We have plenty of time for questions. So I don't see any raised hand. So in the meantime, what do you think about questions? So I have a couple of questions. So the first one, so you said that you used Eurosita data to find candidates. These were the only 2 candidates you found, or there were more candidates?
Okay, let's put it this way. If one would put candidates into tiers, these 2 were the best ones, and the second tier is really, it's not linearly worse. They are just much closer to the noise, and you go to tens or hundreds of objects which are impossible to follow up, and they're most likely just normal spurious detections above the Eddington limit. So the point is, these eruptions last half an hour or a few hours, and we have a 4 hours gap in the sampling. So in order to have a significant difference between the detections in the high state and in the low state, we really need to be somewhat lucky with the sampling and the actual light curve of the QPE. So at the moment, I would say that these are the only two candidates in the first tier of operations, just because it's observationally too expensive to follow up the second tier, which is then just a collection of potentially just normal AGN-like variability, all in all. Yeah.
Okay, you were lucky because you had two candidates and both of them were.
Yes.
Confirmed. Yeah, that's great. We have a question by Linda.
Very nice talk. I am not of the field at all, so maybe this question, but I'm just raising to your challenge to provide new or to give new
yes,
possibilities for the model. So I'm working on cataclysmic variables, and actually dwarf novae have a similar behavior. So we have these dwarf nova outbursts, and there are some which happen every couple of days, and there are some which happen every year. So there are different periodicity in there, and they are also kind of periodic, not quite periodic, but kind of periodic. And the reason for this is well, very much established by now, and is instability of the disk that is only stable at a certain mass transfer rate. So if the disk has a certain temperature and a certain density, then the disk is stable, the accretion disk. Whereas if the disk is too thin, let's say, then you don't have the accretion mechanism, and it takes a while to actually increase to get to this stability, and only then you accrete everything in one go. So there's this disk instability model. And I was wondering if something like this could be the case, so that it's not actually induced by a change of accretion, but just by how the accretion actually goes onto the black hole in the last
Yes,
moment.
it's actually, it was proposed in a slightly different flavor. Let me just go to the extra slide. Yes. If I remember correctly from the CVs, the instability occurs because the outer region, in the outer region, hydrogen ionizes, and then there is some sort of heat in front. Is this something like that? For
Yes,
CVs?
indeed. Exactly, yes.
And there are models that propose some similar, qualitatively similar instabilities in the inner regions of accretion disk, in which the difference is just that radiation pressure dominates, and therefore there is a different energy balance between what you heat and what you cool, and you might undergo these periodic instabilities, which are shown here from a model. This is what the theory predicts, in which you have a slow buildup of matter until you trigger this instability, and then the inner region depletes, and therefore you have a sharp decay. So yes, people have been proposed accretion disk stability indeed. The point is mainly twofold. As you can see from the bottom right here, data suggests that there is a fast rise and slow decay, and the theory of this type of instability predicts the opposite. So it's quite hard to reconcile this. And in another way, without going into many details into this plot simply tells you that if we use the theories as they are, the type of variability that we observe in QPEs, their periodicity, their amplitude, and their duration is inconsistent, because they vary. They're very too fast for being 10 to the 5 and 10 to the 6 solar mass. So if we take the theory as it is, this would the periodicities and the duration would look like they are 10 solar mass or 100 solar mass black holes, which on the other hand would be impossible to reconcile with the 10 to the 43 ergs per second at the peak that they are making. So this simply tells you that current instability models like this are not the answer. If there are future ones which are improved and they can explain this would be indeed still a possibility. Yes, that's a very good point.
Okay, cool. Thank you.
Thank you.
We have a question from YouTube by Marianne Hayda. So the question is, well, first of all, very interesting talk. The periods of the known systems seem to fall in a pretty tight range. Is that real, or is it very difficult to detect longer period systems?
So you probably meant the distribution across the different sources. It's within a few hours and a day. Yes, I think I showed it at the start somewhere. Yes, indeed, there are a few limitations. Let me try and think whether I can avoid using any model for this. So yes, for example, from the point of view of a typical observation, even if you use, for example, XMM Newton, which is the one that can perform the longest continuous observation, it lasts for about a day. So any period longer than that, it would be impossible to be observed. For example, this is the typical XMM Newton observation. So if the period is of the order of this observation, then it's probably very hard to detect them. And I think if they are indeed some orbital phenomena, probably any period shorter than this is not possible, because maybe then the tidal radius and the ESO goes inside the innermost stable circular orbit, and then you can't really have orbits around 10 to the 5, 10 to the 6 of black holes. If that's not the correct model, then in principle one could have arbitrarily low periods. But yes, there is an upper bound on this. And in fact, it could be that black holes with higher masses might do something similar over much longer timescales and periodicities, and they would look like just what people, for example, might be calling changing Locke. And I don't know, it's just a speculation, but yeah, I don't know the answer to that at the moment.
And we have an additional question in YouTube by Thomas Webers. So if there is time, could you elaborate a bit on the detection algorithm that you're using?
Yes, you mean, I guess Thomas means for the Rosetta search.
Yes.
So effectively, it's some sort of, so practically speaking, if I only see one bright Eero day, this could be anything, this could be a TD, a gamma reverse. So for practical reasons, I would need two. Then the code essentially computes a maximum amplitude variability. For people which are not familiar, you just take the highest rate and the lowest rate in a light curve, and you quantify the significance of this difference. The difference that my algorithm takes into account the time dimension. I want to know, I want to have a amplitude variability in which not only it repeats at least twice, but also, for example, the two high states have low states in between. This is just a technical difference between a normal, I guess, flare detection algorithm and what I'm doing. But it's mostly for practical reasons, because otherwise, if there was only one flare, it would be really hard to distinguish it from other type of events from nuclear, galactic nuclei. Yeah.
Great, thanks. I think we need to, yes, we are above the hour, so we need to stop the question sessions. Thanks, Riccardo, again for this very interesting talk, and also Emma. Both talks were very, very interesting. With this, we end this Hypatia Colloquium session. Thanks all for coming, and see you in the next time. Bye-bye.
Thanks a lot. Goodbye.
Thank you.